last lecture we discussed about geometrical path and optical path and the significance of optical path. Okay, now let's do a few problems and then we will discuss some other interesting aspects of interference. Okay, look at the problem, a very simple problem, the standard case that we discussed in the last lecture. Okay, let's see what we have. I have this normal. You see, this is the normal YDSE setup. Normal. Okay. What is the meaning of normal here? The normal means the screen is kept parallel to the slits. These are the slits. The screen is kept parallel. Okay. This is normal setup, and the light is incident normally. This is normal YDSE setup arrangement. All the values are given. Now, a thin plastic sheet of thickness T and refractive index mu is pasted over one slit. Okay, so here I am pasting this one thin plastic sheet here. Refractive index is given and thickness is given. Okay, we understand this is special case. This is standard case. All the effects that is going to happen, central bright fringe is going to change. Along with that, the whole pattern is going to shift up. Okay. Now the first question itself, if mu is this, then what is minimum thickness to get maxima, minima at center? It's like this, at this point here, the geometrical path of both these waves are same, okay? But optical path is not same. Okay? The optical path difference is significant, is important in calculating phase difference. Okay, at this point optical path difference is equal to mu minus 1 times t. It is not equal to 0. It will be 0 only if mu becomes 1. If that means if there is no sheet here, then everything is air. In that case only. Now, so if it is not 0, it can be anything. Okay. Now what I want is I want a maximum. Okay. So first part A for maxima, okay, this path difference should be equal to either 0 or lambda or 2 lambda or like this. 0 is not possible. That means this corresponds to minimum. Okay, that means mu minus 1 times t minimum is equal to lambda. Okay, that's it. So T minimum is lambda. What is lambda? It is given 4000 angstrom over 1.5 minus 1. This becomes 8000 angstrom. That's it. That's how we solve it. Now, for minima, delta x should be either lambda by 2 or 3 lambda by 2, okay, or multiples of half lambda. This corresponds to minimum, okay. So here I will have mu minus 1 and t minimum is lambda over 2, okay. So t minimum is lambda is 4000 angstrom, okay, over 1.5 minus 1 times 2, okay, it becomes 4000 angstrom. Okay, so if the thickness of my sheet is 4000 angstrom, in that case, at this position here, at the center, I will get a minimum. If it is 8000, I will get a maximum, okay. A maximum, a bright fringe, but it is not central bright fringe because path difference is not 0. Okay, now, if mu is this, then and central, okay, so central bright fringe is going to shift. Okay. So now what it says is that if mu is this and central bright fringe is formed in front of one slit, then find T. Now if I paste a sheet here on the upper slit, then whole thing is going to shift up. If I paste it here, whole thing is going to shift down. So central right fringe will also shift. Okay. So what it says is that the central right fringe is shifted here. So here at this point, in front of this slit, I am getting central right fringe. Okay. That means delta x is 0. Okay. Makes sense? Now, what do I do? What do I have to find? I have to find t. How do I find it? How do I find it? Okay. How do I find it? Path difference here is 0. What is path difference here? It is not 0, it is some value. I do not know. T I do not know. Mu is given, but I do not know t. Okay. This distance I know. What is this distance? This distance is d. Then half of that, this will be equal to d by t. We discussed that when the whole pattern shifts, when I paste this, central right fringe shifts. Along with this, everything shifts up. Everything shifts up. Okay. So whatever were the number of fringes contained here, okay, whatever is the number, 10, 20, 30, whatever. Okay. So if I observe at any point, okay, so those many number of fringes are going to shift up. Okay. And we have a very simple formula. Okay. Number of fringes that shift n is equal to mu minus 1 times t over lambda. That's it. Okay, number of fringes that shift. These many number of fringes will shift. Okay, so shift in position of central right fringe is equal to n times omega. Okay, this will be equal to, okay, so let's calculate this. Okay, this I do not know. This will be equal to n mu minus 1 times t over lambda. Okay, and then lambda capital D over t. Okay. So you either remember this or this. Remembering this is easy. Okay. So we always remember this. Then using this, I can find shift in the position of central right fringe. Okay. If these many number of fringes shift and width of the fringe width is omega, then the total shift will be a number times fringe width. Okay. And this way I can calculate very easily. So here it is given, so this is equal to mu minus 1 times t times lambda gets cancelled, capital D over t. And this is given. It is in front of one slit, that means it is equal to d by 2. Okay, so d over 2 is equal to mu minus 1 into t. Okay, mu minus 1 into t, capital D over t. Now I have t. I want to find t, so I can find thickness. Let's see. Okay, the answer is going to be interesting. Let's try to figure out. This t is going to be equal to d square over this t is going to be equal to d square over 2 times of mu minus 1 into t. Now this d small d is given 1 mm. 1 mm. Okay, so it is going to be equal to 1 mm is going to be equal to the square of that 10 minus 6 over 2 times of 1.2 minus 1 times d is also given 2 meters. Okay, it is 2 meters. This will be equal to this much meter. This much meter. Okay, now this is equal to, this is 2 and 2 4 and 2 8. Okay, so this is 1 over 0.8 micron. Now think about this. What type of thickness it is? Is it a large thickness or is it a small thickness? What it is going to be? 1 over 10, 0.8, so 10 over 8, so 5 over 4, it is 1.25 micron. 1.25 micron. This is a very small thickness, Okay. Now what it tells me is that I can actually use YDSE to find very small distances, very small thickness. Okay, if I have a plastic sheet of this thickness, 1.25 micron, 1 micron, which instrument are you going to use to measure that? And measure that correctly? Very difficult. Okay, very difficult. Okay. But carrying out this experiment, this simple experiment, you just make a setup of Young's double slit experiment. Okay, you find the fringe pattern, you just and then paste this plastic sheet here. Just find how many fringes shift through a given point, and that's it. You can find this thickness, and this method is actually used extensively. An excellent method of finding very small distances. We use interference experiments. Okay, this is an experimental technique. It is even used in the industries also to find small thicknesses, small distances. We use interference experiment. Okay. Now the next one. If 20 fringes pass through a point on a screen after pasting, okay, so I think this should be fine. Okay. You see. So the second one also is like this. So already given 20 fringes pass through a point on a screen after pasting the sheet, then find the t if you use 1.4. Okay. So directly I can write this t is going to be equal to n lambda over mu minus 1. That's it. This is thickness. Okay, let's see, let's calculate. This is 20 and 4000 angstrom. Okay, this is lambda and then mu 1.4 divided by 1.4 minus 1. Okay, so this is 8 times, this is 8 times 3 and 1, 4, and then 10 power minus 10, 10 minus 6 over 0.4. Okay. This becomes 20 micron. Okay, 20 micron. That's it. Okay. So easily we can find such small distances, such small thicknesses using this experiment. Okay. Now the next one should be simple. Okay. YDSE is carried out in air. Okay. YDSE, let's say that this is my YDSE. It is carried out in air. Wavelength is given. Wavelength is lambda. If whole setup is immersed in a liquid, okay, everything I am immersing in a liquid. Everything is immersed in a liquid. Okay, then find mu. Okay, different conditions are given. Let's first start with this. What is effect on fringe pattern? Position of central right fringe. Okay. Before I fill up this whole thing, what is delta x? Delta x here at the center, delta x is 0. Okay. That means I get central bright fringe. I get a bright fringe, path difference is 0, so I call it central bright fringe or 0 order maximum. Now, if I look at these two waves, they are traveling same distances. Okay. Their geometrical path are same, optical path are also same because both are in air. Now, if I fill up this whole thing, with this liquid, then also the geometrical path is the same, optical path is also same because both light rays have same geometrical path and they are passing through same medium. They are passing through same medium, so optical path is also same. So position of central bright fringe, no change. No change. Okay. Now fringe pattern. What is the meaning of fringe pattern? Fringe width. Fringe width. What do you think? Fringe width will change or not? What do you think? Fringe width will change or it will not change? Okay. If the wavelength is lambda here in air, what will be wavelength here in this medium? What will be wavelength here? Wavelength here, lambda dash is equal to lambda over mu. It decreases. Frequency remains constant. Frequency remains constant. Speed changes, so wavelength also changes. Frequency has to be constant. Okay. Frequency, speed is equal to f times lambda. Okay. Lambda. So v over lambda is frequency is constant. If v changes, v becomes 1 by mu times. Speed here is c. Here it becomes c over mu. So this also becomes 1 by mu times. This we have done already. Wavelength changes. Now, if wavelength changes, what is the effect on fringe width? Fringe width is equal to lambda capital D over D. Now, the new fringe width will be equal to lambda dash capital D over D. It becomes omega over mu. Wavelength changes. Wavelength changes. Fringe width changes. Okay. So mark this thing. Note down this thing. If the whole setup is immersed, okay, I will carry out my calculations the same way that I have been doing. Only in place of lambda, I will use lambda dash, the new wavelength. Okay, because the waves that are interfering here, the waves that are interfering at any point, their wavelength has changed. Okay. Do I take into account the optical path difference? No. Both are passing through same medium. Okay. This is a very confusing point. We will discuss about this in a much more detail, in advanced course. Okay. If we discuss it here, then the chances are you will start becoming confused. Okay. In advanced course, we are going to explore this thing in a little bit more detail, or much more detail. Here, let's keep it simple. Note it down. If the whole thing is immersed in the same liquid, same medium, if the medium is not same, then things are going to change. If this ray is passing through one medium, this ray is passing through some other medium, then things are going to change. But that will happen in advanced course, not here. Not here. Okay, so mark this point. If the whole setup, if the medium is changed, if the medium in YDSE setup is changed, instead of air, if it is carried out in some other medium, then you find wavelength in that medium. You find wavelength in that medium and then carry out your calculation, forgetting about the medium. Just in place of lambda, you start using lambda dash. Then everything else will remain same. Everything else will remain same. Okay. Do not explore too much into this at this time. In advanced course, we are going to look at several cases. We are going to explore it deeply. Okay. For now, keep it simple. Just note it down. That if the whole setup, if the medium is changed, then you find wavelength in the new medium and then carry out your calculations in normal way, as if nothing has happened. As if nothing has happened. Okay? Now, let's find out what it is. First of all, what is the refractive index of medium if eighth bright fringe forms at a position previously occupied by fifth bright fringe? At some position, let's say that this position here, at any position, this position here, okay. It was earlier occupied by fifth bright fringe. Now the same position is occupied by eighth bright fringe. Why this has happened? Why this has happened? It is because omega dash has changed. Fringe width has decreased. In the same length, now more fringes will be packed. Okay. So the position where I was earlier, I was getting fifth bright fringe. That means in this much length there were 5 bright fringes. Now in the same length, I have 8 bright fringes. It has happened because this fringe width has decreased. Do you understand this point? Okay. So now what it will be? It's like this. Okay. This position is y. This distance is y. This distance is y. If this is a bright fringe, okay, then y is going to be n times omega. N times omega. That means n times omega in air will be n times omega in liquid. In air it was occupied, okay, it was occupying what position? Fifth position. So 5 times omega in air is equal to, now it occupies 8 times omega in liquid. Okay, this will be 8 times omega in air over mu. Look at this, and that's it. That's what I want. Okay, so this gets cancelled. I get mu is 8 over 5 becomes 1.6. Okay, I hope that it is focused well. Okay, we hope that it is focused well. Okay, let me focus it again. Okay, I hope, okay, that it's focused well. I just need to keep on checking this. Okay, anyway. Do you understand this? Next one. What is lambda? If D is this, and fifth dark fringe forms in front of one slit. In front of one slit, fifth dark fringe forms. Okay? Let me draw it here again. Okay, so I'm writing this. Lambda dash is equal to lambda over mu. Okay? Omega dash is omega over mu. Okay, makes sense? Alright. Now let's see. Now, in front of one slit, this is my one slit, S1, S2. In front of one slit here, I get D5. Fifth dark fringe. Fifth dark fringe forms in front of one slit. Okay. What is the position of fifth dark fringe? Okay. We in the previous lectures we did this position of nth fringe from center. Position of nth bright fringe. Nth bright fringe is equal to n times omega. That's it. N times omega. Position of nth dark fringe is equal to nth bright fringe minus half omega. Okay. This becomes n omega minus half omega. So position of fifth dark fringe will be equal to 5 omega minus omega over 2, which becomes 4.5 omega. Okay, and this is equal to d by 2. Forms in front of one slit. Position. Okay, so d by 2 is equal to 4.5 times omega dash. In this medium, in the medium. This is a general expression. In this medium, it will be omega times. Okay, this will be equal to 4.5 times omega over mu. Okay, makes sense. Now everything is given. D is given, all these things are given, mu is given. I want to find lambda. Lambda I want to find. Okay, I will write this. It is like this 1.5. So D is given. Okay, let me write it this way. D over 2 is equal to 4.5 over mu. This is lambda capital D over small d. That's it. We have the answer. So lambda, this is what I want to find. I want to find lambda. It's like this. D square. D square. Let me write it this way. D square. Mu times D square. Mu times D square. Mu times D square over 9D. Over 9 capital D. Does that make sense? Is that fine? Is that fine? I hope that it is fine. Okay. So lambda, this I want to find. D square. Mu D square over 9D. Okay, that's fine. Now mu is 1.5 times 1.5 times. Okay. D square. Small d square 0.9 times 0.9 times 10 minus 6 divided by 9 times 1.5 capital D. Okay, we use all the values. So here it is. This gets cancelled. This becomes 0.1. Okay, so it becomes 9 and 10 power minus 8. So 900 angstrom. 900 angstrom. Okay, that's fine. Answer is fine. What do you conclude from this? What do you conclude from this? Okay. This simple experiment, very simple, innocuous, innocent experiment, using this, I can find wavelength of light. Think about it. Think about the power of this. Forget about solving problem. You are going to solve problem today or tomorrow. Of course that is going to happen. The problem solving, of course you are going to do. If you keep on making your effort, you are going to solve it. At the same time, you also start appreciating the subject, the beauty of science. Do you wonder how scientists are able to find the wavelength of light, something that is invisible? How they are able to find the refractive index? What experiments they carry out? How do they find such small thicknesses, 1 micron thickness? Something is 1 micron. A virus is 1 micron long. Bacteria is 1 micron. How the hell do they find out? Using such experiments. What else do you think they do? This is what they do. Using this simple setup, I can find wavelength of light. In the interference last year of mechanical waves, we discussed some methods where we can find the wavelength frequency of sound waves using simple experiments. Okay, that is the power of science. You should be in a position, you should be able to appreciate this. If you are not able to appreciate it, you have to think a little bit harder. Okay, make some more effort. Okay, so we almost concluded this chapter. You see, there are many things. Okay, if you join the advanced course, you will see that how these things can take different turn. Okay, many interesting things will come. The basic principle remains the same. Basic principle never changes. The foundation remains. This is foundation. We are never going to change it. Never ever we are going to change it. Okay? We will add few things, but we are never going to subtract anything. Nothing. Okay? All right. Now, the last thing, a very interesting thing, that is known as very interesting. Okay, it's like this. Okay, very simple. We just have to study the theory. Later on, we will do problems also in advanced courses. We will do a few problems, but here we are concerned only with the theory. Okay, the theory. Okay, the topic is interference from thin films. Thin films. Okay. First of all, what is the meaning of thin films? Okay. Films having thickness of the order of wavelength. Wavelength, okay, lambda. I have this thin sheet, thin film. Okay. Thin film. This thickness is T. Now this thickness is comparable with of the order of lambda, like few lambda. Okay. Few lambda is equal to few lambda. It's not like the wavelength is 1000 angstrom, 4000 angstrom, and this thickness is 1 meter or 1 centimeter. No, very thin film. Okay, on this thin film, light ray is incident. Let's say this is the light ray. Light ray is incident. Okay, the medium of this film is, let's say, me. Medium is me. Okay. Now, at this point, the medium changes. So what will happen whenever the medium changes? Some part is reflected. It always happens. Whenever medium changes, some part of the light is going to be reflected, and the remaining part is refracted, transmitted. Okay. Now, at this point, the medium changes again. Again, the medium changes. Now, here also, some part will be reflected. It goes back in the medium, and then some part will be reflected, refracted, transmitted. These two light rays will be parallel shift, lateral shift. Okay, again, here medium changes again. Here medium changes again. Okay, and here also some part will be reflected back in the medium, and some part will be transmitted. Okay. Here again, some part is reflected, okay, and some part is transmitted. Okay, understand this? Now, this is the incident light. Let's say this is first light, first part at this point, and this is second part. Okay, at this point, the light ray divided into two parts. One part is reflected, the other part is transmitted. Now, this transmitted part, after reflection, okay, it reflects again, and then this is transmitted. Okay, it is the same light here, Now, if I keep a screen here, then these two light rays will interfere. Okay, these two light rays will interfere. Okay, this is interference between reflected light. Reflected light. Okay, one part is reflected from here, the other part is reflected from here. Okay, we will get a fringe pattern. We will get a fringe pattern. Here also, here if I keep a screen here, and here also I'm going to get interference pattern, fringe pattern. These two light will interfere. It will interfere. Okay, here also interference will happen. Interference between transmitted light okay, all right, and if white light is used, white light is incident on film, then it results into colorful fringe patterns. Okay, for example, okay, the bright colorful patterns formed by soap bubbles. Okay, this is the first example. Have you seen the soap bubbles floating in air? And if you look at them, they appear so colorful. that is the fringe pattern. That is the fringe pattern. Okay, because it is floating in white light. So white light is incident, and then it gets reflected, and here we receive these two lights. They form interference pattern. We are seeing that interference pattern. That is nothing but the fringe pattern of interference happening between these lights, reflected light. Okay, so that colorful pattern of that soap bubbles is because of this interference from this thin film, okay, or formed by soap bubbles, or second, okay, the bright colorful pattern, okay, of oil floating on water. Here also, you see, if I have a thin film of oil, you see, if I have this container, or even if on the floor, you must, I'm sure you must have seen it. If you drop a few drops of oil on floor, on a smooth floor, the oil quickly spreads. And if you look at from one particular angle, then it appears very colorful. It is because of this. Okay. So let's take this example of this oil floating on water. So I have this thin surface of oil. This thin surface of oil, this is oil, and this thing is water, okay. And light is incident like this, let's say. Light is incident. Now some part is immediately reflected, and some other part is first transmitted, then reflected, and then it comes out. Okay. And if you are looking from here, you will see the interference pattern. These two interfere, okay, depending on this wavelength. Okay, at different angles, different type of patterns will be seen. Okay, at one particular angle, it appears very colorful. I'm sure you must have seen it. So it is because of the fringe pattern here that is formed because of interference. Okay, now what are the conditions? Okay, let's write the conditions here. First here. Okay. Now, this interference is happening between which light? Okay, let's look at this. Let me. Okay, let me do this here. This is 1, this also is 1, okay, this also is 1, this also is 1, it gets out like this. 1, 1, 1, like 1. Some part of it is like, let's say 3. It was 2 here, it was 2 here, so let me say this is 3. Interference is happening between 3 and 1. Okay, now conditions, okay, assuming normal incidence, assuming not normal but near normal incidence. Now, what is the meaning of near normal? Okay, the light is incident like this. It is almost normal. Okay, you see. Okay. So in that case, this distance here will be approximately equal to t. It is approximately equal to t. Okay, now between these two light rays, what is path difference? What is path difference? Okay, with respect to this light, this light has traveled what extra path? T and t, 2t. But it is traveling 2t in this medium, refractive index mu. So what will be optical path? It will be equal to mu t plus mu t. It is equal to 2 times of mu t. Okay, you understand this? Now for bright fringe, this delta x should be equal to 0 or lambda or 2 lambda or like this. Okay, 0 is not possible. This is not possible. It becomes possible only if either t is 0 or mu cannot be 0. Okay, so either t is 0. That means there is no thin film. If there is no thin film, then there is no question of interference. That means path difference cannot be 0. Then it can be either lambda, 2 lambda, 3 lambda. Okay, so what will be minimum? Okay, delta x minimum is equal to lambda. Okay, that means 2 mu and t minimum is equal to lambda. Okay. That means t minimum is equal to lambda over 2 mu. Okay. So if I want to see interference pattern for this transmitted light, then minimum thickness should be this, lambda over 2 mu. Okay, what about bright fringe? Okay, this is for bright fringe. What about dark fringe? What about dark fringe? Okay, it will be delta x should be lambda over 2, 3 lambda over 2, okay, 5 lambda over 2, like this, odd multiple of lambda by 2. This corresponds to minimum. Okay, so this I have 2 mu and t minimum is equal to lambda over 2. What should be t minimum? This lambda over 4 mu. Okay, so if I have this thickness, exactly this thickness, then there will be destructive interference, dark fringe. I will not see anything. In this case, I will see bright fringe. This is interference between transmitted light. Okay. Now, what is interference between reflected light? This is little different. Okay, we have to do it carefully. Okay. Now, if you remember something, okay, try to recall last year in the chapter on traveling waves, we were discussing this thing of reflection of a wave from a denser medium, from a rarer medium. When a wave is reflected from a denser medium, it undergoes a phase change. Okay, when wave is reflected from denser medium, it undergoes a phase change of pi. Okay, corresponding phase change of pi, which is equivalent to a path difference of, you see, delta phi is equal to 2 pi over lambda into delta x. Okay, so this is pi is equal to 2 pi over lambda into delta x. Delta x will be equal to lambda over 2 or lambda over 2. When that happens, when wave is reflected from denser medium. Okay, this light is also reflected, but it is reflected from rarer medium. This is air here. This is air. So this will not undergo any phase change. Okay, so we have simply written the normal condition for bright fringe and dark fringe, because there is no additional phase change. There is no additional path difference. Try to understand this. A very tricky point. Very tricky point. Now, if you compare this light, this wave, second wave and first wave. Okay. At this point, this light is reflected. It is reflected from a denser medium. Reflected from, this is air, it is air here, and this is a denser medium here. Now this will undergo immediately, it will undergo a phase change of pi, which is equivalent to a path difference of lambda by 2. That means a path difference of lambda by 2 is already created here. Already created. Then look at the other wave. Okay. Now the other wave, this is the other wave. Now this is traveling this extra distance. This extra distance. It is equal to 2 mu times t. This delta x is 2 mu times t. Here also mu times t, mu times t. 2 mu times t. Okay. There is already a phase difference of lambda by 2. Now, what additional phase difference is needed for a bright fringe? Okay, for a bright fringe. Okay, there is already a phase difference of lambda by 2 already present here. What additional is needed such that constructive, you see, for constructive interference here, what should be path difference? It should be lambda. 0 is not possible. 0 is not possible. It should be lambda, 2 lambda, 3 lambda, and the multiple of lambda. 0 is physically not possible. This is always positive. So the next minimum is lambda. Out of that, lambda by 2 is already present. So what additional I will need? Additional I need only lambda by 2. Okay, so that means for bright fringe, this 2 mu times t should be equal to either lambda by 2. Okay, understand this, or 3 lambda by 2 or 5 lambda by 2, like this. Okay, so t minimum, this will correspond to minimum. T minimum will be equal to lambda times 4 mu. Conditions have reversed. Conditions have exactly reversed. Now for dark fringe, 2 mu times t is equal to, it cannot be 0. It already has a path difference of lambda by 2. So even if this path difference is 0, then also there is going to be a destructive interference. But this cannot be 0. It is 2 mu times t. It cannot be 0. So what is the next possibility? It is lambda. It is lambda. There is already a phase difference of lambda by 2. Okay, so if the phase difference here is multiple of lambda, then it will result into odd multiple of lambda by 2. It is going to be destructive. Okay, so lambda by lambda, it will be 2 lambda, 3 lambda here. This corresponds to minimum. Okay, so I have 3 minimum is equal to lambda over 2 mu. Interference between reflected light. carefully, very carefully. You have to understand this, why it's happening. In exams, questions are asked. You have to think very, very carefully. And this happens, this type of reversal happens only if it is reflected from a denser medium. A denser medium. Only then, otherwise it will not happen. Okay. So that's it. That's it for this lecture and this class and this chapter. Okay, solve problems. Let's discuss it wherever you face difficulty. And then next lecture in sequence will be diffraction. That also is you see this chapter interference and the next chapter diffraction and polarization. All of them are part of what we call as wave optics. Okay. So the next part chapter is also in continuation. So we are again going to discuss the same thing, interference and all. But now there is a different name, diffraction. We will see how diffraction is different from interference and what are its special properties which requires it to be discussed separately. We will see in the next lecture.